Ever tried, like, spotting a firefly right next to a giant spotlight?
Nope. Can't say I have.
Well, that's pretty much the challenge astronomers face when trying to see planets around other stars.
Oh, yeah, I get it. The star's just so incredibly bright it drowns out everything else.
Exactly. Makes you wonder, how do they even find these planets?
Well, for a long time, it was all about those sneaky little clues. Like watching a star wobble slightly.
Like it's doing a little dance because of the planet's gravity.
Exactly. That's how we confirmed those very first exoplanets back in the 90s. No direct images, just these indirect hints.
But now we have NASA's James Webb Space Telescope. Talk about a game changer.
Oh, absolutely.
Not only is it capturing direct images of these faraway planets, but it's giving us a whole new understanding of them.
Incredible.
We're talking young, giant exoplanets in systems like HR 8799 and 51 Eridani.
Right, the ones we've heard so much about lately.
Exactly. And we're diving deep into the latest findings from the Space Telescope Science Institute and a fascinating study just published in the Astrophysical Journal.
So we're getting the inside scoop, basically.
Consider this your express ticket to a cosmic breakthrough. We'll uncover how Webb bypasses that blinding starlight, what these images tell us about these young planets, and most importantly, what it means for understanding how planets form, including our own.
Sounds like quite the journey.
It is. But first, let's really grasp the sheer mind-blowing difficulty of actually seeing an exoplanet.
Right, because it's not like pointing a telescope and saying, there it is.
Not even close. Think thousands, sometimes even tens of thousands of times brighter.
Whoa, that bright.
Imagine trying to see a speck of dust near a lighthouse from miles away. That's the scale we're talking about.
So even with those first exoplanet discoveries in the 90s, directly imaging them was still a pipe dream.
Absolutely. It took over a decade of technological leaps to snag that first direct image.
Which leads us to Webb and its, well, let's be honest, incredibly cool tech.
For sure. Like this thing called a coronagraph.
Coronagraph. Sounds complex.
Oh, it is. Imagine like blocking the sun with your hand to see something beside it.
Yeah, I get that.
But this is like that on a ridiculously precise level.
So like a super precise sunblock for the telescope.
Basically, it's a mask within Webb's near-infrared camera, NIRCam, that blocks the star's light.
That's amazing. So it's literally eclipsing the star to reveal what's hidden around it.
Exactly. Suddenly those faint planets, reflecting light or emitting their own infrared glow, pop into view.
Incredible. So where do these new images take us first?
First stop, the HR 8799 system. It's been a hot topic in astronomy for a while.
I've definitely heard of it. Isn't it famous for having multiple giant planets?
You got it. 4 massive gas giants orbiting a relatively young star.
Young in astronomical terms, I presume.
Oh, yeah. Picture this. HR 8799 is about 30 million years old.
30 million. Our solar system's, what, 4.6 billion?
Right. These planets are practically babies compared to our old Earth.
Wow, so they're still glowing from their formation, basically.
That's the beauty of it. That leftover heat means they emit a lot of infrared light.
And that's perfect for Webb, right? It sees in infrared.
A match made in the cosmos. So Webb, with its coronagraph, blocks the star and captures those infrared glows from HR 8799's planets.
Okay, now for the million-dollar question. What did they find?
Drum roll, please. Significant amounts of carbon dioxide in the atmospheres of all 4 giants.
Seriously? That's huge.
It's a major clue for piecing together how they formed.
I can imagine. But how do they detect something like carbon dioxide from so far away?
Think of it like a fingerprint. Each gas interacts with light in a unique way.
Oh, right. They have those spectral signatures.
Exactly. And Webb's NIRCam not only takes pictures, but also measures the light at different infrared wavelengths.
So they analyze the light to figure out which gases are there.
Precisely. And in this case, they got a clear signal for carbon dioxide, even hints of carbon monoxide too.
That's amazing. And this carbon dioxide, it tells us something about how these planets were born, right?
It does. More carbon dioxide likely points to a gradual buildup, not a sudden collapse.
I see where you're going with this, the different formation theories.
Exactly. When we talk about how gas giants form, there are 2 main contenders, core accretion and disk instability.
So like 2 different birth stories for these planets.
Right. Core accretion is like a slow and steady race.
Okay, how so?
Imagine dust grains in a young star's disk. They bump and stick, forming bigger and bigger clumps.
Like a cosmic snowball effect.
Exactly. Eventually, a core gets massive enough, it starts pulling in gas like crazy.
And boom, you've got a gas giant like Jupiter or Saturn.
That's core accretion in a nutshell. Now, disk instability is more of a dramatic collapse.
Oh.
It's like a dense part of that disk just suddenly becomes unstable.
Unstable how?
Like its own gravity becomes too strong. It can't hold itself together anymore.
And so it collapses in on itself.
And fast. That rapid collapse forms a giant planet.
So one is gradual, the other is a rapid collapse. Fascinating.
Right. And the carbon dioxide in HR 8799's planets seems to lean towards core accretion.
Because of those heavier elements.
Bingo. Carbon and oxygen. Seeing so much carbon dioxide means these planets have more heavier elements than expected.
And that fits with the core accretion idea.
Because if they formed from a quick disk collapse, their composition would be more like the star itself, mostly hydrogen and helium.
Right, so the carbon dioxide suggests they gradually gobbled up more of those heavier elements over time.
Exactly. Like the lead author of the study, William Holmer, said, by spotting these strong carbon dioxide features, we have shown there is a sizable fraction of heavier elements, like carbon, oxygen, and iron, in these planets' atmospheres. That likely indicates they formed via core accretion.
So these observations strongly support the core accretion model for those planets.
They really do. It even lines up with the idea of high metallicity.
Metallicity, right? Like how much of the stardust they've got.
Exactly. Not just metals, but all elements heavier than hydrogen and helium.
And core accretion would lead to a higher metallicity.
Makes sense, right? Those heavier elements would have concentrated in those initial solid cores.
So it's pointing towards those giants forming, much like we think Jupiter and Saturn did.
Fascinating, isn't it?
It is. And it wasn't all about HR 8799, was it? Didn't Webb look at 51 Eridani too?
It did. It captured a beautiful image of 51 Eridani b, the planet in that system.
Which is a bit closer to us, right? 97 light years compared to HR 8799's 130.
That's right. And while this specific study focused on HR 8799's atmospheres, seeing 51 Eridani b directly.
It shows what Webb can do, right? Direct imaging of these planets.
Absolutely. It opens up a whole new window into planetary systems.
It's incredible. I mean, think about how we usually study exoplanet atmospheres.
Through those transit events, when a planet passes in front of its star.
Yeah, and we analyze how the starlight changes as it passes through the planet's atmosphere.
But Webb's doing it through direct imaging. That's revolutionary.
It really is. It means we can study planets that don't even transit their stars from our viewpoint.
It's like suddenly we have this whole new set of tools to understand these distant worlds.
And that brings us to the bigger picture.
Sure.
Why should we care about how these gas giants formed?
Right, because they're way out there. What does it matter to us here on Earth?
Well, as William Ballmer said, and I love this quote, our hope with this kind of research is to understand our own solar system, life, and ourselves in the comparison to other exoplanetary systems so we can contextualize our existence. We want to take pictures of other solar systems and see how they're similar or different when compared to ours. From there, we can try to get a sense of how weird our solar system really is, or how normal.
Wow, that's a powerful way to put it.
It is, isn't it? Like we're trying to understand our cosmic family history.
By studying our distant planetary relatives.
Exactly. And by seeing which formation models are more common, like core accretion versus disk instability.
We get a better grasp of the sheer diversity of planets out there.
Precisely. We've already discovered thousands of exoplanets indirectly. Knowing how they form helps us categorize and understand them.
So it's all about fitting those pieces of the puzzle together.
Absolutely. And the team behind this study, they're not stopping here.
Oh, I bet they're just getting started.
They're planning more Webb observations to really nail down how these directly imaged planets formed.
And they're even looking to differentiate between giant planets and brown dwarfs.
Right, those failed stars that are kind of in between planets and stars.
Exactly. So Webb's helping us refine what we're seeing around these stars.
It is. As Laurent Poyot from the Space Telescope Science Institute, a co-leader of this research, said, we have other lines of evidence that hint at these four HR 8799 planets forming using this bottom-up approach. How common is this for planets we can directly image? We don't know yet, but we're proposing more Webb observations to answer that question.
So they're using Webb to answer some of those big, fundamental questions about how planets form.
They are. And Remy Sommer, also from STSCI, a key figure in Webb's coronagraph operations, added, we have been waiting for 10 years to confirm that our finely tuned operations of the telescope would also allow us to access the inner planets. Now the results are in, and we can do interesting science with it.
Imagine the dedication and innovation it took to get to this point.
It's truly inspiring.
And just a reminder for our listeners, the James Webb Space Telescope is a collaboration between NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA.
It's a testament to what we can achieve when we work together.
It truly is. So let's sum this all up for our listeners. Webb's ability to directly image those young exoplanets in the HR 8799 system and find all that carbon dioxide.
It gives us incredibly strong evidence that those gas giants likely formed through core accretion.
That slow and steady buildup, just like we think happened with Jupiter and Saturn.
And this discovery helps us understand how common this core accretion process might be across the galaxy.
Because comparing these systems to our own tells us so much about our place in the grand scheme of things.
It makes you realize how much we still have to learn about the universe.
It really does. And it makes you wonder, if gas giants can form like Jupiter and Saturn and other systems, what else is out there?
Right. Could there be Earth-like planets forming in similar ways around other stars?
It's an incredible thought. And as Webb continues peering into those distant realms, who knows what other secrets it will uncover?
Perhaps we'll find even more evidence for diverse planetary systems, each with its own unique story to tell.
It's an exciting time to be exploring the cosmos, that's for sure.
Absolutely. And with Webb leading the way, we're sure to make even more groundbreaking discoveries in the years to come.